This section represents one of the hardest parts of biochemistry. We will start off with reviewing the basics of equilibrium. Equilibrium results from the fact that most chemical reactions are not unidirectional, but rather reversible. By convention, the forward rate of a reaction is given by a rate constant of 1, and the reverse reaction would be a rate constant of -1. The equilibrium constant for the reaction is equal to the rate of the forward reaction, K1, divided by the rate of the reverse reaction, K-1. Because we cannot actually measure those rate constants, the way that we determine the equilibrium constant is by measuring the concentration of each of the products and reactants in molarity. These molar concentrations are raised to the power represented by the coefficient of the reaction. So in this example, C, big C, in square parentheses, to the little c power. The square brackets represent concentration in molarity, and I must stress molarity. To experimentally determine an equilibrium constant, what we would do is mix together 1.0 molar of each reactant and 1.0 molar of each product, allow them to react at 25 degrees Celsius, and then measure the final concentration of each product and reactant after equilibrium is reached. The problem with this in the biochemistry context is that if we have 1.0 molar protons, and protons are not uncommon as products or reactants of biochemical reactions, the pH would be 0, which is a pH that is incompatible with enzymes and life. Consequently, biochemists use a modified standard state indicated with a prime, and the prime designation that we would run the reaction at pH 7, holding everything else at 1.0 molar and 25 degrees Celsius. With that background, we can talk about the equilibrium of water. Recall at the end of last section that I said that water is weakly ionizable. The equilibrium is shown in the reaction on this slide. Weakly means that not very many water molecules ionize in this way. At pH 7, the proton concentration is 1 × 10⁻⁷ molar. This means that 1 out of every 10 million water molecules is ionized. And because when water ionizes, we always get an equal number of hydroxide and proton ions, then the ion product is 1 × 10⁻⁴, which is the basis for the pH scale, which goes to pH 14. The next piece of information we need to think about is pK values. For acetic acid, which is a common biochemical molecule, the KEQ is equal to the acetate concentration times the proton concentration divided by the water concentration and the acetic acid concentration. But it turns out that the concentration of water is a constant at 55.5 molar. This can be determined by taking the density of water, 1.0 grams per milliliter, and dividing it by the molecular weight of water, 18.0 grams per mole. If we are careful with canceling out the units, this will give 55.5 molar. This concentration is so high that it really cannot be altered in the process of biochemical reactions. Since it is a constant, we can multiply the KEQ by the water concentration to get a Ka, which is the acid ionization constant. For acetic acid, the Ka prime is 1.74 times 10 to the minus fifth, unitless number. This is not a particularly easy number to work with, so biochemists more frequently work with pKa values. The pK is the negative log of the Ka. So the log of 1.74 times 10 to the minus fifth is minus 4.76, and therefore the pK is the negative log, or 4.76. As mentioned above, Ka values are not something that can be measured directly, and instead we would be experimentally determining them. If I start with some pH, pH 1, for example, hydrochloric acid, and then neutralize that hydrochloric acid, I would see a linear rise in pH as I added hydroxide, as shown in the blue graph on the left of this slide. In contrast, if I do the same thing except start with acetic acid, which may have a pH of 1 or something like that, and I add hydroxide, I would see an initial rise in pH just as I did with HCl. However, I would then see the pH stop rising for a while and then resume its rise after some amount of base has been added. This flattening of the curve is referred to as buffering and represents the pKa value for that acid. So experimentally, I can determine the pH of 4.76 by drawing a line from the midpoint of that horizontal line over to the pH scale and determining what that pH is. And then by taking the anti-log of minus 4.76, deduce that the Ka value is 1.74 times 10 to the minus fifth. So a buffer is a compound that does not allow the pH to change even if acid or base is added to the system. And biochemically, one of the very important molecules which buffers pH is bicarbonate, HCO3-, which is an amphiprotic compound. Amphiprotic compounds are those that can act as either a proton donor or as a proton acceptor. An equation to memorize for biochemistry is the Henderson-Hasselbalch equation, which is used to determine the pH of buffered solutions. It is expressed in two alternate forms as shown here, and I personally like to use the A-HA form of the equation. But this is a personal preference, and you can use either one that you are most comfortable with. A very important concept relating to the Henderson-Hasselbalch equation is that when the pH is equal to the pK, there is an equal amount of A- and HA forms of the buffer. This is shown fairly simply with the following proof, and I present it as a way of making sure that if you are rusty at working with logarithms, that you look at least a couple examples of how we use these mathematically, which is going to help you in solving these buffer problems. Because this topic represents one of the hardest parts of biochemistry, I wanted to do several problems to get you familiar with the approach I would use in performing calculations of these types. The first question is, what will the pH of a solution be if 0.1 milliliters of 6 molar HCl is added to 100 milliliters of water. This is a problem that you should have done in freshman chemistry, but to refresh your memory, pH is equal to the negative log of the proton concentration. Using the unit cancellation technique, which you must never forget, it can be determined that this represents 0.0006 moles of protons in a volume of 0.1 liters. And you should work through that math to make sure that you can do it. Mathematically, this works out to be a pH of 2.22, being rather sloppy with my use of significant figures. This pH is incompatible with life, other than it is a pH that would be present in your stomach, where food is being digested. Since in biochemistry we want to buffer our solutions, the second question is, what will be the pH of a solution if 0.1 milliliters of 6 molar HCl is added to 100 milliliters of 1 molar Heap's buffer, initially at pH 7.6? We always need to know what the pK of buffers are, but we don't want to have to memorize these, except for those that we use every day. So we would look at a table and determine that the pK of this buffer is 7.6. The second point is that in the last problem, we determined the moles of protons, which is the same for this problem. Third, we can calculate how many moles of buffer there is, which in this case is 0.1 moles. Fourth, I am making this problem simple to begin with by choosing a buffer where the pH is equal to the pK value, and therefore there is an equal number of A- and HA, as we discussed previously. Therefore, and that's what those three funny dots mean, there is 0.05 moles of A- and 0.05 moles of HA. Next, we have to set up an equation that describes the chemical change that would occur, and I have written that out on this slide. An important point is that whatever amount of acid that we are working with, we are always going to add it to one buffer species and subtract from the other buffer species. Because protons are positively charged, if they are being produced, they are going to react with the A- form of the buffer, and the A- form will therefore decrease in quantity. In the reaction between the A- and H+, more molecules of HA are formed, and that number will then increase. The only other tricky part of this is sometimes acids are being produced and sometimes acids are being consumed. Once we have determined these things, we can plug the numbers into the Henderson-Hasselbalch equation and find with this particular problem that the pH is essentially unchanged at 7.59. But there is an issue with this particular problem, and that is osmotic strength. Remember from the previous video that an increase in osmotic pressure develops when solutes are added to water. An experiment you may have done in freshman biology is to take cells and put them into water and watch them pop. And if you put them into high salt, watch them shrink. To make a long story shorter, if I use 1 molar buffer, I will cause an osmotic shock and eventual death of the cells. Therefore, A better question is the following question, which is essentially the same problem, other than I am using 50 millimolar heaps instead of 1.0 molar. The amount of acid is still the same, and for this problem, I will introduce a little trick that makes this go faster, of using 0.6 millimoles as the quantity of acid. Second, by the same token, I am going to calculate that there are 5 millimoles total of buffer. Third, since pH equals pK, there will be 2.5 millimoles of A minus and 2.5 millimoles of HA in this reaction. The relevant equation is given at the bottom of this slide. 2.5 A minus plus 2.5 HA plus 0.6 H plus. What we see is that the 0.6 millimoles of H plus will react with the 2.5 millimoles of A minus to yield final amounts of 1.9 millimoles A minus and 3.1 millimoles of HA. This is a good place to say that I have also ignored the volume of buffer in these problems. It really doesn't matter because the buffer is in the same volume, and therefore as a shortcut, I can deal just with the millimoles rather than millimolar. Plugging these numbers into the Henderson-Hasselbalch equation, we see that the final pH is 7.39. This is a larger pH change than in the last problem, but it is not a pH which is incompatible with life, and we avoid crenation of the cells. The last problem gets at the tricky part that I alluded to earlier. Always be thinking about whether acid is being produced or consumed in your reaction. I did take a little liberty in this problem in that if the pK value is not exactly at the starting pH, mathematically my answer will change slightly. However, to focus on the big picture, let us assume that the pH is near enough to the pK value that we can assume that we have an exact amount of A minus and HA. As these problems have demonstrated, the pK value is critically important to choosing a buffer, and we would want to choose a buffer that has a pK value within half a pH unit of where we are doing our experiment. A question students commonly ask is, doesn't that mean we would always be using MOPS or heaps buffer as we did in the last problems? And the answer is not necessarily. If I want to examine protein degradation at pH 4.5, I might use acetic acid as my buffer since it has a pK value of 4.76 as we saw earlier. Secondly, to avoid osmotic shock to your cells, we would often be using a concentration of around 50 millimolar. As you read the biochemical literature, you might see some people using 10, others 25, and others some other concentration, depending on the experiments that are being done. Finally, if you are a student who is interested in working in biochemistry professionally, you should realize that there are some other considerations, such as whether the buffer molecule will chelate metal ions, be an effector of your enzyme reaction, and other possibilities.